stuff. Just a note that today's material will not be on exam 1. Today's material will not be on exam 1, which you're taking next week, right? Today's material will go on exam 2. We still have to talk about it today because we can't just blow off the rest of class, right? So this stuff that we're talking about today will not be on exam number 1. It'll go on exam number 2. Okay, the material stopped for exam 1 on Wednesday. Okay, so everything through Wednesday of this week is exam 1 material. This starts exam 2 stuff. So if you're keeping track of that in your notes. All right, so we've already talked about electronegativity and what it is. We use this Greek letter chi to represent electronegativity because electronegativity is a big long word, whereas that's just one letter, nice and convenient, right? Electronegativity is a measure of how greedy your atom is, right? How good are you at sharing electrons in a covalent bond? We've already talked about this. This is something you already know because we talked about this when we did Lewis structures. And just remember, review, going across a period, electronegativity increases, right? Going down a group, electronegativity decreases. And what's the most electronegative element? Fluorine, right? Fluorine is the most electronegative element. So this is all stuff we talked about already. And this figure is in your textbook on page 316. Okay, you have this exact figure in your book, page 316, giving the exact electronegativities. Okay, you're going to need this to do your next homework set. I'm going to wait a couple days to post your new homework. Right, you've got homework due tonight of last week's stuff. I'm going to wait a few days to post this homework just because you've got an exam coming up. Okay? But I'm just telling you right now, you'll need to refer to that page when you're doing that homework set. All right, so electronegativity is going to have an impact on covalent bonding, right? Because if two atoms are sharing electrons and one of them's pulling them closer to them, right, that's not going to be even sharing. So if you're bonded to yourself, you're obviously going to be sharing equally, right? Because even though fluorine's the most electronegative element, this fluorine's going to pull on electrons just as hard as this one is, right? So if this is representing electron density, right, fluorine to fluorine, that's going to be even sharing, right? Versus hydrogen and fluorine, right? Look at the electron density on hydrogen, look at the electron density on fluorine. The electrons are way closer to fluorine than they are to hydrogen, right? So this is the scenario we're talking about today. Unequal sharing, and what does that look like for us as chemists? So we have to calculate bond polarity. Now I'm referring to a specific bond, okay? Just a single bond between two atoms, okay? Might be a double bond, but you know what I mean. One atom pair. All right, so let's use our figure on page 316. If you have your book with you, you can pull it out. So let's calculate the bond polarity for a sulfur-hydrogen bond versus an oxygen-hydrogen bond. Now, before you do any arithmetic, you should be able to predict which one of these is going to be more polar just because you can look at the periodic table, right? Which one of these should be more polar? They're both being bonded to hydrogen, so you're comparing sulfur versus oxygen, right? The math supports oxygen, but does the periodic table? Yes, so oxygen's more electronegative than sulfur is, right? So even if you didn't have your table on page 316 handy, just by comparing and looking at the periodic trend, you would know that this would be a more polar bond than this would, okay? Just from basic periodic trends. So here are the cutoff points for what we call polar, nonpolar, and ionic bonds. Okay, so if electronegativity difference, okay, this is the Greek letter delta, uppercase delta. Delta means change in, right? So final minus initial, if we're talking about like delta H, right? We're going to be using this symbol a lot this semester. Delta means change in, okay, or difference in. So if the difference in electronegativities is 0.4 or less, we're calling it nonpolar, and it's still covalent, right? Covalent means that they're sharing. If the difference in electronegativities is in the range of 0.5 to 1.7, we're calling it covalent still. It's still a covalent bond, but it's not being shared evenly. So that means it's polar. Polar means it's got a positive side and a negative side, right? So there's one atom that's going to have a positive partial charge and one atom that'll have a partial negative charge. Because electrons are negative, right? And if they're all hanging out, or most of them are hanging out on one side versus the other, that gives that side a negative. Obviously, the other side would be positive. And then if it's greater than 1.8, they're not being shared. Okay, those are not shared electrons. This is an ionic bond, so they're not being shared at all. A cation is giving electrons to an anion, and there's no sharing whatsoever. So here's what electron densities would look like, right? Even sharing, unequal sharing, and then no sharing whatsoever. Does this make sense? Make sense? Make sense? There's the same figure, just from a different textbook. All right, so even sharing, uneven sharing, and then no sharing, right? Notice there's a difference. In polar covalent, it's a partial positive and a partial negative, whereas in ionic, that partial sign goes away. It's just a charged cation and a charged anion, right? That's not partially negative, that is negative. Whereas this is just partially negative, okay? Make sure you understand the difference there. All right, so we represent bond polarity using these symbols. This is the lowercase delta, right? You just saw uppercase delta a minute ago. Lowercase delta looks like an 8 that you got lazy and you forgot to close. Okay, so that's a partial negative, okay? Like I just showed you here, right? That's a partial positive and a partial negative. So that would be partial negative charge. This would be a partial positive. And then we draw this little symbol with a plus sign, and basically just draw a plus sign and then keep extending it, okay? And so the plus sign is next to the positive end, and it's pointing towards the negative end, okay? The partially negative end, I should say. So you just draw this little plus sign, and you just keep going with an arrow pointing towards the partially negative region. All right, so electron density maps are something that we draw to show where electrons are spending their time. This is something we'll do next week. We're going to channel our inner kindergartner. We're going to do some coloring to show electron distribution. Okay? Notice this one is polar covalent. That's why it's got partials, whereas this one's straight up ionic. Those partials are gone. Okay? Red means high density, and blue means low density. So notice if we're looking at H2, that's why it's red straight down the middle, right? Because it's being shared equally. So all the electrons are between the two nuclei, right? That's why this one's red. We're looking at HF, right? Notice it's red over here, and it's blue over here. And then in AF, right, it's the whole piece is red, and this whole piece is blue. So we're going to do some of this next week. We're going to be looking at electron density maps and correlating that to the things we're talking about today. So nonpolar, polar, and ionic. Do we understand these three ways of looking at electrons and where they're hanging out? Yes? Okay, let me ask you this question. Why is this green? How come it's all green, no red? Right, it's shared with yourself, right? If you're sharing electrons with yourself, it's going to be pretty straightforward. Okay, now these are sample problems, all right? We're not going to go through them now in class, but it's fair game for your next homework set. So if I give you a bond and ask you to classify it, right, you would use your table, calculate the difference in electronegativity, and look at those cutoff points that I gave you, okay? So for instance, you could predict this, though, just by looking at the periodic table. Would you predict this to be a big difference in electronegativity or a little difference in electronegativity? That's big, right? That one's ionic. This one you should be able to predict, no calculation needed, right? This one would be polar, nonpolar, or ionic. That'd be nonpolar, right? What would you predict this one to be, looking at periodic table? Carbon-oxygen bond. Think it'd be covalent and polar, or nonpolar and covalent, or ionic? It's two nonmetals, so it's not going to be ionic. Do you think a carbon-oxygen bond would be polar or not? Is carbon far enough away from oxygen? Yes, it's polar bond. What would you expect for this one? I mean, this one's a metal and a nonmetal, so you should know right off the head. That's ionic, right? And then what would you expect this one to be? Look at sulfur and selenium on the periodic table. What would you expect that one to be? Covalent and nonpolar. The electronegativity difference there's 0.1. If you ever come up with a negative number, just take the absolute value, because the sign here doesn't matter, okay? So if you just switch the order, that makes that go away. So just take the absolute value if you ever get a negative number. Now this is something really important. You need to jot it down somewhere, commit it to memory. You need to know that the electronegativity of carbon and the electronegativity of hydrogen are essentially the same. Because remember, hydrogen is way over there, but we pretend in terms of electronegativity, it's in this region. Okay? Hydrogen's 2.1, carbon is 2.5, so the difference between them is 0.4, so a carbon-hydrogen bond is non-polar. Okay? That's super important that you know. Okay? You need to know that a carbon-hydrogen bond is non-polar. We're going to be looking at a lot of molecules that involve carbon-hydrogen bonds. Make sure you know carbon and hydrogen, non-polar. Okay? Make a note to yourself. You've got to have that one just committed to memory. Okay, so this is bond polarity, right? We're just looking at a single pair of atoms sharing electrons, right? That's bond polarity. Is a bond being polar the same thing as an entire molecule being polar? No, okay? Bond polarity and molecular polarity are two different things. You can think of a bond polarity like, you know, analyzing your arm, whereas molecular polarity is like analyzing the whole person, right? This would be one bond, but then all of you collectively would be a whole molecule. Okay, so this is just individual bond polarity. Now let's look at molecular polarity. This has a big bearing on what we're doing next week with intermolecular forces. So we're going to spend some time talking about molecular polarity now. So molecular polarity asks, does the molecule as a whole have a partial positive end and a partial negative end? That's what molecular polarity asks us. Okay, bond polarity looks at a single pair of atoms, which could be part of a bigger molecule, right? The entire molecule being polar or non-polar. That's what we're looking at with molecular polarity. Does everyone see the difference between bond polarity and molecular polarity? Yes, yes, yes. All right, so here are the two requirements for a molecule to be polar. It first has to contain polar bonds. Okay, if all the bonds in that molecule are non-polar, then by definition, that molecule has to be non-polar. And then number two, it has to be asymmetric in its electron density. I'll show you lots of examples of this, because really the best way to learn it is just see lots of examples. And then if you don't meet these two requirements, then you have to be non-polar. So you could have polar bonds, but not meet this requirement. So if this one's checked and this one's not checked, then that molecule will be non-polar. If both of these are checked, those are the two requirements for a molecule as a whole to be polar. Okay? Got to contain polar bonds, and then the electron density has got to be asymmetrically distributed. Again, this is just kind of you need to practice. So we're going to look at lots of examples today, and I think you'll start seeing the patterns. Is everybody good on the two requirements for a molecule to be polar? Am I going too fast? Or too slow? Everybody asleep? Might be asleep just because you don't want to learn chemistry. I don't know. Okay, so just like when we represented bond polarity, we use this little notation, right? We're going to do the exact same thing we do with a molecule, except now it's going to be on a bigger scale, right? You're only going to have one partial negative region, one partial positive region. We're looking at the molecule as a whole will point towards the negative region. So just like a plus that you just kept going, right? Pointing towards the negative region. Region being the key word versus atom, right? In the bond polarity, we were pointing towards the negative atom. Now in the molecular polarity, we're pointing towards the negative region. Okay, so let's do CO2. Let's start with carbon dioxide. So first thing you have to do is you've got to draw its Lewis structure, right? And then if you look at its VSEPR theory, in terms of VSEPR, what's its shape? This would be what? Linear, right? So this is linear using VSEPR theory, so it's a straight molecule, right? Now, here's why this is a non-polar molecule. This bond is polar, right? A carbon-oxygen bond is polar, yes? So we've got a vector, you know, think back to like physics, you've done some vector math, right? This vector, this direction, but then you've got one exactly the same, this direction. Okay, so because these two vectors are equal and just pointing in different directions, is there a net positive side or negative side? No, right? Because this bond is just as polar as this bond. So while these bonds are polar, they are offsetting each other. Does this make sense? Carbon dioxide is a non-polar molecule. It contains polar bonds, but as a whole, it is a non-polar molecule. Does this make sense? Okay, because this vector offsets that one. Everybody good on CO2? Starting with some simple ones, working our way up. All right, boron trifluoride is also nonpolar for the same reason, okay? So a boron-fluorine bond is polar, right? This is the negative, this is the positive. This one is polar, fluorine, 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 right? So this is this one, this one, this one. Those three are all polar bonds, but they are equal to each other, right? They all offset each other. There's the electron density map for BF3, right? There is no net region where it's positive like or negative, right? They're all offsetting each other. Does this make sense? All right, now let's substitute one of these fluorines with a hydrogen atom. Now we have HBF2. That changes things. That changes things significantly, right? Because a boron-hydrogen bond is nonpolar. So that part, that's nonpolar up here. But these two parts down here, that is still polar. So now we do have a region down here where this has greater electron density than up here. Does this make sense? So when we draw our arrow indicating the direction, it'll look like this, right? We're pointing down towards the negative. So this is our partial positive region. This is our partial negative region. The reason we're spending so much time on diagnosing this is because next week, when we do intermolecular forces, if you can't decide if the molecule is polar or not, you won't be able to do the next step, okay? So look at this and make sure you understand why this is a polar molecule, but the previous one wasn't. Any questions on this one? Okay, once we substitute out one of those fluorines for a hydrogen, that changed things. Everything's different now. So this is a polar molecule. All right, think about this one. Is methane CH4 polar? That be a polar molecule or non-polar molecule? Think about it for a minute, and then we'll go over it. Okay, what do we think? Is methane a polar molecule? Yes or no? Is a carbon-hydrogen bond polar, number one? No, carbon and hydrogen have the same electronegativity, right? The electronegativity difference is 0.4. So methane has nonpolar bonds, therefore there's no way it could be a polar molecule. All right, think about this one. Fluoromethane, CH3F. Take a second, sketch the Lewis structure, decide what you think about that one. Okay, let's go over fluoromethane. Polar or non-polar? What do we think? This one's polar, right? Because now we have substituted a fluorine where we had 3 hydrogens originally, right? These are all non-polar bonds. This is a very polar bond, right? So if you are drawing the Lewis structure, you would point this way, right? This is the positive, partial positive region. This is the partial negative region. If you made a mistake, you see where you made it. Okay, this is so important for next week. So we need to make sure we understand this, because if this doesn't make sense, you're going to have a lot of trouble next week when we do intermolecular forces. Okay, now if you've got lone pairs on the central atom, that creates an area of high electron density, right? Because if you've got lone pairs are electrons. Therefore, if you've got lots of lone pairs, you're going to create high electron density on that central atom. So let's look at water, right? Everybody from biology is taught water's a polar molecule, right? I think that's like lesson number 3 of biology. So let's talk about why water's polar. We already know the answer. If you've taken bio ever, you know the answer. So let's compare it to CO2 just as a reference. So here are our 2 Lewis structures, right? What immediately jumps out? You say, okay, polar bond, that's polar bond, that's polar bond. But what's the big difference here, other than, you know, hydrogen smaller than oxygen? What's the big difference that should jump out to you? When you draw the 3D structure of this, are these going to be the same shape in 3 dimensions? No, this one's going to be linear, right? This one's going to be bent, right? It's based on the tetrahedral molecular geometry. Good job. Right, so those two lone pairs, that's high electron density, right? That takes up a lot of space. So those two lone pairs give a lot of extra. If you're drawing it red, right, it'd be red right there in the middle. So water is polar. You have a positive, negative arrow going this way and a positive, negative arrow pointing this way. Right? So in water, you've got 2 partial positives and 1 partial negative with 2 arrows pointing up. Right? So yes, water is a really polar molecule. Really, really polar. We're going to talk about this in great detail next week. Okay, take a second and try these. Formaldehyde, PCl5, and ammonia. Bet you're experts at it. So, formaldehyde, polar or non-polar? 50-50 chance. It's polar, right? That's polar molecule. PCl5, polar or non-polar? Non-polar. Ammonia, polar or non-polar? That one is polar, right? Because of the lone pair on the central atom. It's a high electron density area, plus that's a polar bond, that's a polar bond, that's a polar bond. So it is pointing in this direction. Okay, now, polar molecule is another word for dipole, okay? When you hear the word polar molecule, you should know that this is a synonym for dipole. We're going to talk about dipoles a lot. So make sure you understand that a polar molecule just means dipole. Nothing special about dipole that isn't the same in a polar molecule. It means the same thing, right? Di means two poles, right? A positive and a negative. So polar molecule is a dipole. So dipole moment, now you guys know this Greek letter. What's that? Who remembers? Cow says, right? Okay, so this is a quantitative measure. You can actually calculate dipole moments. You calculate a value for dipole moment. And so this is something to quantify how polar a molecule is. So the larger the value of dipole moments, the more polar the molecule is. Now I'm not going to make you calculate dipole moments, but I do want you to interpret it. So I've got one of my fun stickers up here. Dipoles have a moment, do you? Dipole moment is of great use to us as chemists, right? Because it quantifies how polar our molecule is. As this value goes up, the polarity of the molecule increases. So I won't make you calculate it, but I would ask you to explain it. So let's go through some examples of things I might ask you to do. So these are all linear molecules, right? They're all 2-atom molecules. HF, HCl, HBr, HI, H2. Those are all super simple molecules, right? So here's the dipole moment. What's going on? Explain this trend. Decreasing. It is decreasing. Why? Why is HF more electronegative than HCl, which is more electronegative than HBr, which is more electronegative than HI? Right, you're just reading straight down the periodic table, right? Fluorine's more electronegative than chlorine. Chlorine's more electronegative than bromine. Bromine's more electronegative than iodine. And why is this one 0? Bonded to itself, right? Okay, explain this trend. H2O versus H2S. That's a pretty significant difference, right? 1.85 versus 0.95. Both of these are bent. So what's the reason here? Periodic table might help. Sulfur is what? Less electronegative, right? And this next week is something we'll talk about with intermolecular forces. Okay, look at this trend. NH3 versus NF3. There's a big difference in electronegativity here. Oh, they're both trigonal pyramidal. Wow, that's a huge difference. That's a humongous difference. NH3 versus NF3. This one you might have to think about a little bit more. Why is that such a humongous difference? Right, so nitrogen's pretty electronegative and fluorine's pretty electronegative, right? So the electronegativity difference throughout is way less than it is here. Good job. Okay, this one's the hardest probably of the ones that we're looking at today. So I'll give you a second to think about it. CH4 and CCl4 being 0, that one's easy. Why is CH3Cl more polar than CH2Cl2 or CHCl3? They're all tetrahedral. So take a second and think about that one. Because if I don't give the values and I just say pick the most polar one, your average student will pick this one and say, because there are 3 chlorines. That's what the average student would say. And that's not the most polar one. It's actually the least, if we're excluding the 2 nonpolars, right? Can anyone come up with an explanation? If you're good at vector thinking, then this answer is pretty straightforward. Right? If you've taken physics and you've done vector math. Right? Can anyone explain this trend? Thoughts? All right, let's look at the Lewis structure, well, the 3D structures, I should say. Right? They're all tetrahedral. Okay, so here we've got 1 chlorine and 3 hydrogens. When we add that second chlorine, it actually cancels half of the effect of this one, right? So when we had a super focused region here, now we've distributed that across 2. Does that make sense? So your vector goes from being intense to being more, it's a lot less intense now, right? And then when you add that third one, right, we're distributing it across 3. So I mean, you can just look at the arrow, right? Does this make sense? When you've added that third chlorine, this third chlorine is reducing the effect of the 3 as a whole. And that's not what your brain naturally thinks, right? Most students would say, oh, this one's got 3 chlorines, it's got to be most polar. When in fact, of the 3, it's the least. Does this one make sense? Yes, yes, yes. All right, that's where we'll stop for today. So I hope you have a great weekend, and I'll see you Monday.